We're going to do a review problem about Ampere's law. To start with, this is what Ampere's law actually is. It is that the contour integral of the magnetic field around some contour is equal to the current that is flowing through the surface whose boundary is that same contour. So if the surface's name is S, that boundary is little delta del S. That surface is the boundary of S. That surface is the boundary of S. You can also write this as just equal to I, the total current through the surface. So if that's Ampere's law, let's pick a problem and do an example. So let's say we have a long cylindrical conductor whose axis is along the z-axis. And whose radius is A. And inside it, it has a current density J equals Z hat J naught e to the minus R. And we're asked to find the magnetic field everywhere. We start by looking at the symmetry of the problem and seeing, can we actually apply Ampere's law to this problem? I mean, it says right at the top of the page that we're going to do an Ampere's law example, but check the symmetry first. So there's no angular dependence. And there's no z dependence, since this is a long cylinder. So the only dependence in our problem should be on R. Now that doesn't mean that the magnetic field is R-directed. That means that the amplitude of the magnetic field, or the magnitude of the magnetic field, only depends on the radial distance from the z-axis. What is the direction of it? Use the grab the current technique. And then if your right thumb is along the current, then your fingers are pointed along the direction that the magnetic field should point. Which means here, the magnetic field is phi hat directed. So far, so good. So if we are going to apply Ampere's law, we need to define a surface and its associated boundary contour that can be used to solve this problem. So let's look at Ampere's law again, because this is the thing that trips people up kind of a lot. We need to do the integral of h around some contour and set that equal to the current flowing through a surface. Well, that means this is not like Gauss's law where we'd want to choose a closed surface to enclose the whole thing. This is more like we want to take a slice that is perpendicular to the direction of current flow. And then do these integrals in the cross section of the problem. So if we were to take a look at what's going on this cross section, we would have a circle of radius A, and there is non-zero current inside the circle, and there is zero current outside the circle. And the current that is inside the cylinder is coming out of the screen right at us along the Z direction. So we want to define our Amperian contour so that it's useful for solving the problem both for radii less than A and for radii more than A. So there's going to be two different regions in the problem. There's going to be R less than A and R greater than or equal to A. And we need to know what is the magnetic field for both of these. So what we're going to do is we're going to define our contour to be a circle of radius R, and that radius can vary. Circle of variable radius R. All right, so that's our Amperian contour. Remember that a contour has a direction. We need to make sure that the direction of the contour agrees with the direction that we define the surface normal vector. We're going to choose the surface normal vector to be Z directed, plus Z, because that agrees with the current and that makes it easier to avoid sign errors. So ds is along plus Z. And if we're going to do that, that means that our contour has to circulate around counterclockwise. So dl is along phi hat. With all that in mind, we can actually set up our integral now. So on the left-hand side, we've got the closed contour integral of h dot dl. Now h, we've said, only depends on r, and we're going to fix r along a circle of radius r. So that's going to be the integral from 0 to 2 pi of phi. There we go. H is a function of r. Phi hat dot dl, which is phi hat r d phi. That just gets us 2 pi r h of r, and we still haven't identified h's r dependence yet, so we're going to leave it like that. On the right-hand side of Ampere's law, we had the integral of the current density through the surface. Now that current density was z hat j naught e to the minus r, and the differential surface element is going to be z hat r, not r squared. The differential surface element is going to be z hat r dr d phi. I'm going to tell you a fact right now, and that's that the integral of x e to the x, or e to the minus x dx, is equal to x minus 1 e to the minus x. You can work this out yourself using the product rule for integrals. But I don't really want to do it right now because I'm trying to save time. So, but using this fact, we can write down that this whole thing, if we integrate the 0 to 2 pi integral of d phi, and nothing depends on phi, so that just gets us a factor of 2 pi. We've got a j naught, which came out to the front because that's a constant. Then we've got the integral along r to deal with, and that gets us r minus 1 e to the minus r. That's being evaluated from 0 to r. It's a little confusing. We should have made these r primes to begin with so that that would be easier to deal with. And once we evaluate that, we've got 2 pi j naught r minus 1 e to the minus r minus 0 minus 1 e to the 0, which is 1, so plus 1. This is true for r less than or equal to a. Once we get up to r equals a, then, for r greater than a, j is equal to 0. So if r is greater than or equal to a, then we have to substitute in a for this varying value of r. So we have a minus 1 e to the minus a plus 1 for our two different values of the current flowing through our enclosed, through the surface that is enclosed by that contour. And on the left-hand side, we just had 2 pi r h of r, like that. Which means that h has two different solutions, one for r less than a and one for r greater than or equal to a. So h, which is a function of r and also a vector, is equal to phi hat j naught over r. I'm just going to leave the r over here because that makes my life easier to deal with. R minus 1 e to the minus r plus 1, like that. Or phi hat j naught over r, a minus 1 e to the minus a plus 1. And the top solution is for r less than or equal to a, and the bottom solution is for r greater than a.